In previous videos, you learned the important concepts of vector bases and span. This means that we are now ready to break free and think of vector spaces as much more than geometrical arrows. We are going to start the video by looking at different examples. I would like to start with a very colorful example, one which hopefully begins opening your minds to the infinite possibilities. This is a TV screen displaying an image. Have you ever looked at a screen using a microscope? Here is a handheld microscope that can be added to the phone. And if we look at the screen through it, we can see the pixels. Look at that. If you look closely, you will notice that each pixel is composed of 3 different light-emitting diodes of different colors, called subpixels. They correspond to red, green, and blue LEDs. These are the primary colors for human eyes. Each pixel has its 3 LEDs turned on with different intensities. For example, a bright yellow region in the image would correspond to the red and green subpixels turned to their maximum value, while blue is turned off. So doing these color combinations, our eye from a distance sees it as different colors. Knowing this, we can describe the configuration of each pixel as a vector. First thing, we need a basis. So let's choose the following basis vectors. R hat corresponds to the red subpixel turned to maximum brightness, G hat is the green subpixel turned to maximum, and the same for B hat with the blue subpixel. For example, a bright magenta color could correspond to C equals 1 R hat plus 0 G hat plus 1 B hat. But this is a vector basis. We can write any color as a vector C equals R hat plus G hat plus B hat. Or in component form, C equals RGB. This vector space is officially called the linear RGB Colorspace. In it, every color can be interpreted as a vector in a 3-dimensional space. The vector is not representing anything geometrical, it's representing a color. But thanks to maths, we can interpret it and even visualize it as a vector. So here we are doing just that. In the top left corner you see a circle which indicates the actual color, and in the middle you are seeing the vector in the RGB space. You're also seeing the coordinates, C equals 011, C equals 0.711, and so on. Notice that the point 000, the origin, would be black, and the point 111, when the 3 components are to their maximum and equal values, we actually get white. But interestingly, if the 3 components are some intermediate number but they are equal, then we get something between black and white, so we get a gray color. In fact, all the gray scale ranging from black to white is represented by an actual geometrical line in this color space. The line where all the components are equal, C equals lambda times 111. Now we can use the power of vectors to help us calculate things with colors. For example, we can determine the distance from any color to the line of grays, or we could project vectors into the line of grays to find the black and white closest equivalent of any color. As our next example, we will now move to higher dimensions. Consider all polynomial functions of a degree smaller than or equal to n. Let me show you how easy it is to represent these as vectors. Let's choose the following basis: 1, x, x squared, x cubed, all the way up to x to the power n. And now notice how any polynomial of this degree is simply a linear combination of the elements of the basis, with a set of coefficients which can be our vector components. For example, the polynomial x squared can be written as a vector in component form like this. Let's see another example with this other polynomial. So, any polynomial of degree n or smaller can be written as an n plus 1 dimensional vector. This time I cannot draw the vectors accurately, because I cannot draw n+1 dimensions. But you can still do false drawings to help your intuition. For instance, let's pretend for a moment that this 3D space represents the n+1 dimensional space of polynomials of degree n. We could draw the span of x as this line going through the origin, while the span of x squared would be another such line. The span of the two basis vectors x and x squared would be a plane containing both previous lines. Now we can ask whether certain polynomials fall within or outside this plane. For example, the polynomial 3x plus x squared is contained in this plane, while the polynomial 5 plus 3x squared is not. Notice how remarkable it is, being able to think of polynomials as vectors. Let's consider a final playful example. In some video games, characters have attributes such as strength, magic, and so on. Those can be the components of a vector. In this way, each character is a vector. The length of the vector might give a hint about how powerful the character is. The unit vector associated with each character's vector would tell you about what type of character it is. For example, it has much more strength than magic in a ratio of 3 to 1. You could also imagine doing dot products between the unit vectors of different characters to get a number between -1 and 1, indicating how similar the two are. One could say that I am overcomplicating things, because, in essence, we could have just said that a vector can represent any collection of n real numbers, where each number can represent anything, from subpixel brightness to polynomial coefficients. This is true, although to be complete, we can extend it to any collection of n complex numbers, which are also valid vectors. For example, the quantum state of a physical system is a superposition of normalized quantum states forming a basis, in which each basis state has a complex amplitude. You will learn all about this in the quantum mechanics module, but you will need the maths behind it. Therefore, when dealing with vectors from now on, I will always try to consider the possibility of them having complex amplitudes. So what really is a vector? Is it an arrow in space, a collection of numbers, a polynomial? Or are all of these just different manifestations of one same thing? Is there some idealized, abstract notion of what a vector really is? When mathematicians develop linear algebra, they want their conclusions and their tools to be valid in every possible vector space. Whether dealing with geometrical arrows, colors of a pixel, polynomials, or video game characters, mathematicians don't need to know. They want to be able to work with all of them at the same time. For this reason, mathematicians establish a list of rules that any vector in any valid vector space must fulfill. These are called the axioms. In a sense, the axioms define what a vector really is. In this way, mathematicians use axioms as a foundation in which they build a huge construction of results based entirely and exclusively on the axioms. Each new brick in this construction is based solidly on the previous ones by following the rules of logic. If the axioms hold, then everything else will also hold. A famous and beautiful example of this way of doing maths is the book called The Elements, written by Euclid more than 2000 years ago. In this book, all of planar geometry, including theorems such as Pythagoras' theorem, are all painstakingly derived from a set of only 5 simple axioms, which include things such as a line may be drawn joining 2 points, and all right angles are equal. One could argue that this makes maths more difficult and abstract, but the reward for doing it that way is that all of the results and tools developed can be applied to absolutely anything that follows the axioms. The reward of being abstract is that you gain generality. So coming back to vectors, let's be abstract. All of the tools and concepts that we have learned and will learn in the next lessons about linear algebra will be applicable to all the examples of vector spaces which obey the following axioms. Let's have a look. A vector space V is a non-empty set of objects called vectors. So we can imagine this vector space as this bag of vectors. And two operations are defined on vectors. One is addition of vectors, and the other is multiplication by a scalar. Both operations must have mathematical closure, which means that when you apply the operation in any two members of this bag of vectors, the result is also in the bag. For example, adding two vectors in two-dimensional space always results in another vector in the same two-dimensional space. Adding two polynomials of degree smaller than n always results in a polynomial of degree smaller than n. The same idea of closure must also be true for the multiplication by a scalar. Now, we could be even more abstract and ask, how do you actually define the addition of two vectors? Well, it turns out that we have axioms for that too. You can define it in however way you like, as long as it follows these four rules: commutative, associative, additive identity, and additive inverse. Pause the video and take a minute to look through them. Convince yourself that our usual rule for adding vectors by placing them one after the other fulfills these axioms. Similarly, we can ask what is meant by multiplication times a scalar. Again, more axioms. The answer is abstract and therefore general. Multiplication by a scalar is anything that fulfills the following axioms: being distributive over vector addition, distributive over scalar addition, associative, and the existence of the scalar identity. So that's it. These are the two operations and 5 axioms for each operation that really define what a vector space is. Please do not worry about remembering these axioms. They are just a formality that I wanted to show you. However, if I gave you the axioms together with an example of vector space, you should be able to check whether it fulfills the axioms or not. Let's do an example. Let's consider vectors as geometrical arrows in the traditional sense. In this interpretation, the only vector spaces that we have seen so far have been the two-dimensional space and the three-dimensional space. But there are other vector spaces. Consider the line given by the parametric equation r equals r0 plus lambda v. This line defines a set of vectors R. Does this set of vectors constitute a vector space? Or, in other words, does it follow the axioms for a vector space? Initially, we may think that it does, because we can add vectors and we can scale vectors within the line. However, the operations don't fulfill the axioms. Consider any two vectors in the line, A and B. To start with, the first axiom is violated, because there is no closure under addition. According to the first axiom, the sum A plus B should be a vector living in the same space. So it should be a vector in the same line as A and B. However, A plus B clearly falls outside of that line. Therefore, there is no closure under addition. The same happens for scalar multiplication. The axioms are not fulfilled, and so the line r0 plus lambda u is in general not a vector space. The problem is that the line did not include the origin as one of its vectors. But what happens if r0 equals 0? We bring the line into the origin. Then, as if by magic, it suddenly does fulfill all the whole set of axioms. So it becomes a vector space. Let's check that. Consider the addition of A plus B, any two vectors within the line. Indeed, the result always falls inside the line itself. The same can be said for scalar multiplication. Feel free to check that all of the axioms are fulfilled. The line can be seen as a vector space itself. Does this surprise you? I think it should. It means that we can consider a line to be a vector space, just like we were considering the 3D space as a vector space. This is true for any line crossing the origin. The space that these lines form can be written as span of V, where V is any vector in the line. This idea can be translated to lines in 3D space, and also to planes in 3D space. Any plane in 3-dimensional space which crosses the origin, and this condition is very important, can be considered a vector space in its own right. The set of vectors in the plane follow all of the axioms. Such a space can be written as the span of u and v, where u and v are two vectors in the plane. In fact, that is the key. Whenever we can write a geometrical entity as the span of a set of vectors, then the space can be considered a vector space. A line or plane that cross the origin can be written using span of vectors, while a line or plane which does not cross the origin cannot be written as the span of any vectors, and they are not vector spaces. The span of any set of vectors always includes the origin, because the linear combination can have all of its coefficients equal to 0. Any lines, planes, volumes, or higher dimensional entities which can be written as a span of vectors, and therefore which include the origin, can be considered as a vector space. This leads us into the important concept of a vector subspace. The formal definition is simple. A subspace is a vector space that is contained in another vector space. This simple concept is best understood with examples. A line in 2 dimensions is a subspace of the 2-dimensional space. A plane in 3 dimensions is a subspace of the 3-dimensional space. Any line contained in this plane will in turn be a subspace of the plane. We can use Venn diagrams to represent spaces and subspaces. So this is the set of vectors representing 3D space. This is the set of vectors representing plane P, which is a subspace of 3D space. And this is the set of vectors representing line L, which is a subspace of plane P and also a subspace of the 3D space. And remember, the origin is always included in all of the spaces and subspaces. Note that a subspace always has fewer dimensions than the space it is contained in. Well, strictly speaking, a space can always be considered its own subspace, because it is contained on itself. So, okay, in that single specific case, the subspace obviously has the same number of dimensions as the space, because they are the same thing. But in every other case, a subspace has less dimensions than the space it is contained in. As a general rule, if you have a span of n linearly independent vectors forming a space of dimension n, then the span of any subset of them is always a subspace of the original space. So we have seen that vector spaces can represent very different things. The only limit is our imagination and the axioms. However, if vector spaces are not representing real geometrical objects in space, how can we really define the measurement of distances in them? This is the topic of the next video.